Hello students, welcome back. In this part, we are going to learn about the two important parameters of any reaction. One is order, other is molecularity, and how order and molecularity are derived for simple as well as complicated reactions, and also about the differences between the order and molecularity. So let's start with the presentation.
Now let's learn about what is meant by order of a reaction. So we already know what is a rate law. So for the reaction, take this reaction, and for this reaction the experimentally determined rate law expression is rate is equal to K, rate constant, into concentration of A power X and concentration of B power Y. So this X and Y are order with respect to X. X is known as order with respect to the reactant A, and this Y is known as order with respect to B. And the sum of these two is the overall order or total order of the reaction or this given reaction. So order means it is the sum of the powers or indices of the concentration terms appearing in the rate law expression. So if you know the rate law expression for a given chemical equation, then you can add the powers or exponents, and that will give the order of the reaction. So for this equation, the order of the reaction is X plus Y, which is the sum of the powers or sum of the indices of the concentration terms of the reactants, that is A and B. So this is order of a reaction. So once you know the rate law expression, and from the rate law expression you can calculate the order of a reaction. And I already discussed that the X and Y may or may not be equal to A and B, which are stoichiometric coefficients. And let's discuss more about this order. So this order can be order of a chemical reaction. It may be 0, it may be fraction, it may be integer, and in some cases it can be negative also. So let's see some of the reactions in which order is 0, fraction and integer. So this is the first reaction, that is hydrogen and chlorine. Both are reacting with each other and they are forming HCl. So for this reaction, the experimentally determined rate law expression is rate is equal to K, and it is rate is independent upon the concentration of hydrogen and chlorine. Here H2 power 0 and Cl2 power 0. So the sum of the exponents, the sum of the powers is 0. So order of this reaction is 0. So this is an example of a zero order reaction. So for zero order reaction, the rate is not going to be dependent upon the concentration of the reactants. And let's come to the second equation. This is a reaction between hydrogen and bromine, and it is giving HBr as product. So for this equation, for this reaction, this is the rate law expression. So the order with respect to hydrogen is 1, and plus order with respect to bromine is half. So which is 1 and half. 1.5, which is a fraction. So the order, so this is an example of a fractional order equation, fractional order reaction. And order can be negative also. Order can be integer also. So this is example of a reaction in which order is integer. Here order with respect to hydrogen is 1 and with respect to iodine is 1. So the sum is equal to 2. So order of the reaction is 2, which is an integer. So these are examples of zero and fractional and integer order reactions. And in some cases order can be negative also. So one such example is the conversion of ozone into oxygen. So for this reaction, the rate law is, this is the rate law expression, and you can also write it in this way. Rate is equal to K into O3 square O2 power minus 1. Here the overall order or total order is 1, but the order with respect to oxygen is minus 1. So here the order can be negative, but the overall order cannot be negative. Overall order is always a positive quantity, but order with respect to one of the reactant or product can be negative. So in this reaction, order with respect to O2 is negative, but the overall order is still positive. So order can be negative, but that is the order with respect to only reactant can be negative, but the overall order is always a positive quantity. So this is a first order reaction where the overall order is 1. But the kinetics, but this is not as simple as a first order reaction. The kinetics of this reaction is very complicated, and this is an example of a negative order reaction. So this is about order of a reaction, and order can be 0, can be negative, can be fraction also. So now let's discuss about molecularity. What is meant by molecularity of a reaction? So molecularity is the number of reacting species involved in an elementary reaction. So but here what is an elementary reaction? So let's discuss about it. Elementary reaction is a reaction which is occurring in only one step. So in nature we have so many reactions, but all the reactions are not simple. They do not take place in one and only one step. So all such reactions which are taking place in one and only one step are known as elementary reactions. And if the reaction is not taking place in one step and it is taking place in more than one step, say 2 or 3 or 4, then such reactions are known as complicated reactions or complex reactions. I repeat, the reactions which takes place in more than one step are known as complicated or complex reactions, and reactions which takes place in only one step are known as elementary reactions. And in elementary reaction, the number of reacting species involved, and these reacting species may be molecules, they may be atoms, or they may be ions also. So the number of the reacting species which are taking part in an elementary reaction is known as molecularity of a reaction. So let's take some example to understand it better. If you consider the first reaction, in the first reaction, atom A is reacting with an atom B and it is forming a molecule AB. So in this reaction, the reacting species are atoms. And how many species are involved? 2 species. This is one atom and this is one atom. So 2 atoms are involved in this reaction. So its molecularity is 2. And if molecularity is 2, then such reactions are known as bimolecular reaction. Bi means 2. So a reaction can be bimolecular, and this is an example of a bimolecular reaction. And if you see the second example, second reaction, in which there's only one molecule is involved, that one molecule is breaking down into 2 atoms, which is the decomposition. So in this reaction, only one molecule is involved, and this is an example of a unimolecular reaction. Unimolecular, that means its molecularity is 1. If you see the third example, the third equation, in this AB molecule is involved and C atom is involved. So here the reacting species are AB molecule and C atom, and 2 such species are involved. So this is one species and this is one reacting species. So 2 species are involved. So which is again a bimolecular reaction whose molecularity is 2. And in the last example, AB molecule is reacting with a CD molecule. So here also 2 molecules are involved. So this is also an example of a bimolecular reaction. And there can be trimolecular reactions also, where molecularity can be 3 also. In such cases, 3 atoms, molecules or ions maybe react with each other and they'll form the products. So if molecularity is 1, then it's called unimolecular. If it is 2, then it's bimolecular. If it is 3, then that is trimolecular. Let's discuss more about molecularity. The molecularity is always a whole number. It cannot be 0. It is not 0. It is always a whole number. So it may be 1, 2, 3, 4 and so on. It cannot be 0, because 0 means like nothing is involved in a reaction. But in a reaction, at least one reacting species will be involved. So molecularity, the least molecularity can be 1. It cannot be 0. And it cannot be fraction also. Molecularity cannot be 1 by 2. It cannot be 3 by 2. It cannot be 5 by 4. Because the atoms or molecules which are involved during the reaction, they are always integers. Like one molecule can react with 2 molecules, or one molecule can involve with one more other molecule. So but one molecule cannot react with half of other molecule, and one molecule cannot react with 3/2 of other molecule. That means the molecularity cannot be a fraction. It is always a whole number other than 0, and it cannot be negative also. It cannot be negative also. But what about molecularity of greater than 3? Greater than 3. If molecularity reactions which have molecularity greater than 3 are rare, because here the molecules has to collide with each other in order to form the products, which you will learn in collision theory in detail. But the reactant molecules has to collide with each other simultaneously to form the products. So if you see, if you consider this example, if you consider the last example, in this, these two molecules has to collide with each other. As a result, the products will be formed. But the probability that more than 3 molecules will collide simultaneously is very small. Very small. More than 3 molecules cannot collide simultaneously. So molecularity of a reaction which is greater than 3 is rare. Only molecularities up to 3 are very common, and greater than 3 are very rare. Yeah, I told that molecularity is defined for an elementary reaction. In an elementary reaction, it is the number of reacting species involved. But what about molecularity of a complex reaction which is occurring in more than one step? So let's take an example. So this is a reaction. It seems that this is happening in one step, but it is not happening in one step. In fact, it is occurring in 3 steps. So which is a complicated reaction, and each step is an elementary step. So how do you define the molecularity of such complicated reaction? For a complicated reaction, it does not have a molecularity of its own. It does not have a molecularity of its own, but each individual step is going to have its own molecularity, because each is an elementary step. So every elementary step is going to have its own molecularity. So if you consider the first elementary step, here 2 molecules of NO is involved, so its molecularity is 2. And in the second case, like in the second step, the 2 molecules are involved, so its molecularity is 2. In the third step also, the 2 molecules are involved, so it is also a bimolecular reaction. So what we can say here is, this reaction is occurring in 3 steps, and each is an elementary step having a molecularity 2. We can define the molecularity of a complex reaction in this way, and we can also define it in other way, and that is, the molecularity of a complicated reaction is taken to be equal to the molecularity of slowest step, that is the rate determining step. Yeah, you're going to learn about this rate determining step in detail in the reaction mechanism, but now understand that molecularity of a complicated reaction, of a complex reaction, is same as the molecularity of a slow step or rate determining step. So here second step is the slow step, that is rate determining step, and it is having a molecularity 2. So we can say here that this reaction is a complicated reaction, and molecularity of this reaction is 2. Okay, so in this way we can define the molecularity of a complex reaction. Yeah, till now we learned about order and molecularity. So let's find the differences between these two. What are the differences between order and molecularity? Order is an experimental quantity, because order is determined from the rate law, which is experimentally determined one. But the molecularity is a theoretical property. That is, if a equation is given, let's suppose AA plus BB is given, which is giving CC plus DD. Here you can determine its molecularity if it is not a complex reaction, say it is an elementary reaction. So for this reaction, the molecularity is simply A plus B, which you can directly determine from the stoichiometry of the reaction. There is no any experimentally determined thing. And order can be any number, like it can be positive, it can be negative, it can be fraction, and it can be 0 also. But the molecularity cannot be 0, it cannot be negative, it cannot be fraction. It is always an integer except 0. And this order is concerned with the kinetics, that is rate law. But the molecularity concerns with the mechanism, that is the sequence of steps occurring in a reaction. So it concerns with the mechanism, not with the kinetics. And order is assigned for overall reaction as well as each step of the reaction. Like if you take a complicated reaction, then order is going to be assigned for overall reaction as well as for each step of the reaction. Each step is going to have its own order. But whereas molecularity, it is assigned for each step of the reaction separately. Like we already discussed before, that for a complicated reaction, like each elementary step is going to have its own molecularity. So it is assigned for each and every step of the reaction separately. So these are the differences between order and molecularity. So this is about order and molecularity concept of a reaction.
So students, in this part we learnt about order and molecularity and how to calculate order and molecularity of reaction for a simple as well as complicated reactions. So now we are interested to know the concentration of the reactants and products at any point during the course of reaction. So we'll do that in our next part. So stay tuned in.